Okay, we're back in the shop after having been out for a while dealing with more pressing things, but I want to do a little recap of the project that we had for the Rotary Broach. And so far I've got the body completed, and you can see that I've made a brooch, and there'll be another video on how to make the brooch. Also made this little handy dandy little gizmo, which allows you to set the brooch length. And the way that works is you place it on the tool itself and then adjust the length of the brooch out to the stop here, and you'll be at the proper length. Now, last time I had done the video on this, there were a lot of parts missing. I'm kind of new at it and I'm kind of learning, so bear with me. Also made a wrench, small little wrench, kind of easy to make little wrench because none of my wrenches would fit the flat in between the chuck. And so I said, well, easy peasy little wrench, there you go, home and done. Also the brooches, I made a couple of brooches, and this is kind of something that I'm learning how to do and how to heat treat the ends so that they'll hold up to usage. And so far the results have been pretty good. I have done a couple of samples here. This is a 1/4 inch hex hole done in 1018 steel, and you can see it made a very nice entrance and works very well. Good fit to the wrenches. Something else that I learned about wrenches is they vary quite a bit. Again, this is aluminum. Did a couple, four test holes just in aluminum. So good results with the brooch, works very well. But I wanted to kind of recap what we had here. So as you can see, I've changed my design on the grease hole. Counterbored the grease hole, put a small button head screw in there to plug the hole, and I just use a little greasing adapter to put pump grease in there. It's one of these little adapters that you use on vehicles. You hook your grease gun over here and that goes in the hole and pump some grease in, right? But there are some other things that I had not covered. The way to set this up and how to set the length of the brooch. Wanted to show you guys that I've loosened this up. I thought I had loosened it. Hang on a minute. There we go. The way the brooch is adjusted is through this setup here. The brooch is held by an ER20 collet. In the video I said it was an ER16 and I was mistaken. That's a 20. And this is a collet, not an ER20 collet that holds the brooch in place. Now when you're using this thing, there's this considerable amount of force that's being exerted trying to push that brooch into the body. I've never noticed any slip with the collet. These ER style collets hold very, very well. But the design is such that there's a pin that comes into the shank itself, and on the end of the shank there's a set screw, and that's what helps adjust and hold the collet in the body and prevent it from slipping back into the collet holder. After I did that, I said, well, I have to set the length of this brooch so that it reaches the apex of the orbit, and I'll explain that a little bit so you guys understand that. So I came up with this design of a tool here, and it's just a ring of 1018 with some slots here and some button head screws that hold these two little legs. And then the top was machined out so that between this edge here to this edge here is 60 millimeters. And that's the exact length that we need to get that brooch into focus at the apex of its orbit. And that's kind of what I wanted to explain a little bit. So the way this tool works is you either rotate the body or you rotate this part. For instance, if you had this mounted in the lathe, in the tailstock, then this would be stationary. And as you bring it into the work, then this is going to rotate. The way that this works is that you have the center line of the tool body, and then you have a different center line for the broach itself. And the broach sits at an angle to the body, and that's really exaggerated, right? And as the tool rotates, whether we rotate the body or we rotate the broach, what you have is a tool on this end here that's orbiting around a cone. And that action is what causes that cutting action. Now the tip does not move from center, but the edges do this. I hope you can see that on the video. Rolls around like so. So here's the broach, and you can see that as I rotate that around, the cutting edges are actually revolving in a sort of a cone, following the outline of a cone. And since the end of this broach is actually not rotating, the action is such that it does this. And as it rotates around, that's the cutting action that occurs in the hole. Now you do have to make a hole to create this kind of a part. So what you would do is drill a 1/4 inch diameter hole for a 1/4 inch, because from flat to flat, that is the opening that you're going to create. And the tool is going to remove the parts that are outside that concentric circle. Now when you do this, you want to drill that 1/4 inch hole, and then you want to put a chamfer on there to allow the tool to get started into that chamfer. Otherwise, it's going to have a difficult time getting started. All right, but you can see it really makes a nice hole. Now the other thing I was talking about is that here I've got a hex key, and it's a good quality Eklund hex key. And you can see that fits in there very nicely. There's no play whatsoever in there. Nice solid feel to it. Now the hole, the broaches that I've made, from flat to flat, they're 250, 251, somewhere around there. And I did a little research on some of the commercially available broaches, and most of them flat to flat is 252 from there to there. They are resharpenable to some extent, because as you starting to sharpen the end, you can just grind the end flush, come back a little bit, and get a new cutting surface. And what happens is you're going to lose distance between these flats, so your hole gets a little bit smaller as you touch up this grinding. So the next ones I'm going to make, I'm going to push them up a little bit to 252 flat to flat, 0.252. Overall length is 2 inches from end to end. I went a little longer than the standard broaches that are out there. Most of them are, I believe, 1.5 inches from end to end, or 1 3/4 inches. I'm sorry, 1 3/4 inches. I went a little bit longer so that the collet on the tool would have a little bit more grabbing room. And since we have an adjustable length on the broach, it's very easy to compensate for that. All right, so that's the broach tool so far. In the previous video, I had explained how the bearing pack goes in there. There's a radial bearing in the front here, and in the back is a tapered roller bearing, which acts as our thrust bearing. And okay, sorry about that. Had a phone call to take care of. Where were we? I was explaining the bearing pack. Bearing pack, as I said, there's a radial bearing in the front, just a regular ball bearing, and it's metric bearing. It's a 6204 with dual seals when I bought it, and you can see there's one seal in the front here. You can see that. On the back side, I removed that seal, so when the grease goes into the body, it'll grease the front bearing as well as the back bearing. There are no seals on the back bearing. It's a tapered roller bearing, so it gets well lubricated just from that one hole. So that takes care of the broach body and the broach itself. As I said, I'm going to make a video on how to make this hex broach, and I'll probably make some square ones. I'd like to have some square ones too. There's a lot of info out on the web. A lot of manufacturers make these broaches, and they're available in different sizes. For me, the only ones that I really use are the 3/16 and the 1/4 inch. Those are the common ones that I often have a need to make. So that's what I'm going to make. But to make other sizes, it's just a matter of scaling. And then you're off and running. Okay, so getting back to, I want to share some of the things that I ran into when I made this guy. And here's the original drawing that I had for making the bearing cup itself, and this is what I call the pre-bore part, where you're gonna just hog out all this material inside the bore here, and then create your thread for the shank of the tool, and then create the flats right here on the tool for allowing you to put a wrench on there. You chuck this in something that won't mar the shaft, and then loosen the body. I've got a little finger tight now, but when it's on there really good. The other thing I didn't mention is that there's a snap ring in here. I hope you guys can see that. That shows right here, it goes into a groove. And there's some good machining challenges in getting that groove in there, and I'll explain that why in a minute. But that snap ring is what holds the bearing pack in there. If you don't have this, when you retract the tool, the bearing pack comes out with it, because it's kind of a, well, I call it a snug fit in there. I just took a hair dryer and warmed this up to the point where it was uncomfortable to the touch, probably a couple 100 degrees, and then slid the bearing pack in there. And when it cooled off, there's no way I could budge that. But in order to ensure that that bearing pack's not going to wiggle its way out, there's a snap ring that holds that whole assembly in there. So if you should decide to make a tool like this, this would be the start. And all of this was done in the lathe except for the flats. So the body's turned in the lathe. The thread for the shank of the tool is a 118. I chose a 118. I like a finer thread for a tool like this. And that was all done in the lathe. And then you go to the mill. And you could see in the earlier videos that I made on this that the tool, when you, as you can see in the drawing, there's the body itself, and then there's the pocket for the bearing pack. And you can see that the pocket for the bearing pack is canted over this way. And that's what gives you the action of that tool orbiting and creating that cutting action. Now, the center line right here of the body and the center line of the bearing pack coincide at a distance here, and I call that the focal point. when the tool is assembled and you rotate this tool, at the very end there should be no movement laterally. It should be on a point and the tool is orbiting around that point. So like this. And that cone that I was talking about is right here. That's the cone. If you can imagine a cone that is centered on this center line around and coming out this way, that's what creates that cutting action and mystifies so many people. When they see this tool, they say, how does that thing work? And that's how it works. Now, I did research on the internet and found that all of the commercial ones that I found seem to have a 1 degree cone that 1 degree from the center line. So as it rotates around, that angle is 1 degree. So if you think about it, when on this side of the line you got 1 degree, when it comes around the other side you got 1 degree. So that's a 2 degree inclusive motion from that center line. So 1 degree that way, 1 degree that way. Very simple. But you have to think about that, because when you make your broach, the broach is oscillating sideways like this, and you don't want these sides to slam into the hole that you're creating. So you have to create some clearance there. So this tool has a clearance of 2 degrees from the center line. So it's an additional degree from this center line and another additional degree on the other side. So that makes it a 4 degree included angle. So the way that this is made is in a rotary index, and you cant the back of the index backwards like this by 2 degrees, and then you mill one side, mill the other side, and so forth. And I'll do a video on that to show you that. But the trick is really in the heat treatment of this tool. Now this cutter was made from W1 drill rod, tool steel, water hardening tool steel. They call it W1. You can make it from O1 or A2 if you get your hands on round A2. Doesn't matter. W1 is plentiful and cheap, so I went with that. Now the trick is to harden just the very end of this for about 1/4 of an inch. So what I've done is, when I did the hardening process, I chucked this in my drill on a low speed and let it rotate, and I had an acetylene flame there, heating that up till it got cherry red, dunked it in water. At that point, this is so doggone hard, it's got to be at least a Rockwell 60 plus with this drill rod. Very, very hard. None of the files I had could even touch it. It just slipped right off of it, wouldn't even bite it. But at that point, it's so doggone hard, it's very brittle, but only on the end. The back end of this tool is still in the anneal state, so it's got some ductility, and it's not going to break off at this joint. But it's so hard on the end that if you try to do anything like in a 1018 steel or any of the hotter materials, it's going to start crumbling away on you. So you can see, hopefully, the little shadow line from having tempered this a little bit. You can see that straw color on the edges, and that's the trick, to heat the end of this thing so that you get that straw color coming back. You might get a little blue on the front, but straw back here. That's the trick, and I'll show you guys how to do that, how I did it, and it works very well. So far they've held up very nicely in all the test holes I've done. So moving forward, I just wanted to point out some of the things that I ran into and the mistakes that I made when I made the body. This is the second body that I've made. The first one was a major blunder, and I'll explain that in a minute. When you make this pocket that is canted over at 1 degree for the bearing pack, you have to be cognizant of what side you make your offset. Now there's an offset right here. From here to here is 1.05 millimeters. So you have to find the center of the original bore, which is this drawing here. That's the original center of that bore. And then you have to offset that 1.05 millimeters that way. At the same time, this thing is tipped from the back 1 degree. Be cognizant if you do this project not to tip the line on this side. So what I did is I found the center line here and wasn't thinking. I moved my y-axis on the mill this way, and I ended up with a pocket bearing that's pointed out in space this way. So my cone was reversed is what the error was. So instead of having a broach that does this, I had a broach that does this. Not going to work very well. So once I figured out what I had screwed up, got another hunk of steel, came back, rinse and repeat, and here we are. We've got a working tool and come out quite nice. So that's about it for today. Maybe a couple other things I want to point out before we move on to doing the broach. Here's the drawing of the broach. And as I said, this overall length is 2 inches. Originally, I had dished this out in the original design. But what I found is if you dish out the end, you end up with pushing the sidewall of the end of the broach. In other words, you're going to have a loss of material here in that dishing. And consequently, instead of making a nice flat-walled hex, you end up making something like this. That might not be too bad, but it's not what I was after. So, changed my design, and you can see that I had a small dish here. I kind of still had a little bit of dish to provide a little chip clearance here, but I found that a flat-ended broach works quite well because it's tipped at a 1 degree angle, so there is some positive cutting action going on. Now the commercial ones do have kind of a triangular relief here, but the sides are square, and I'll be doggone if I know how they make that. All right, so the angle detail, that was kind of what I wanted to talk about here. Right now this broach is 2 degrees from the center line, so 4 degrees included angle. So when you do this project in the mill, what I do is I use a rotary indexing tool that I have right here. And I know a lot of you probably have one like this. This is a very inexpensive tool. If you hunt around, you can find them. Bear in mind, there's different qualities, and this is a so-so quality, if you want to call it that. But you end up mounting your tool steel in the collet, and you come in here, and this whole thing is tipped this way. So as your tool comes in, it creates the clearance for you. So it's very easy to set. You put a 2 degree angle in the tool, and then you take your cuts. And then all you have to do is measure. You can set the DRO and end up dead nuts where you want to be when you're coming down in the Z-axis to create the flats, the opposing flats. Once you're set, you just go around and do the whole thing. Then I'll go back to the mill, to the lathe, and this chamfer that's on here, I create that back in the lathe. So when I make the blank, I end up with a square end blank here and a turn down stub that's there. I come back and mill that right to the edge of that square edge of the blank, and then I'll take this, go back to the lathe, and turn this right so that we're down to the edge of the tool. Now, a lot of the commercial ones are done by grinding. I do have a surface grinder, but I thought, geez, it would be a heck of a lot quicker and faster to do that in the mill and just use a nice 4-flute carbide cutter, and you can see the finish on that is just beautiful. And so that's how that's done. And like I said, I will do another video on an actual build of this part. So that's it for now. We'll catch you later.